we've been introduced to the idea of arc length for vector valued functions. So we want to extend that concept from, instead of thinking about arc length as something you compute, we want to think about arc length maybe as a function. So we could start at a particular point on a curve and we could see how that arc length grows over time as the t value changes. And so to do that, we can extend this idea. So instead of going from A to B, what we do is we say we want to go from A to some arbitrary value t. So some sort of slider. But we can't use r prime of t dt because you can't have a parameter that you're integrating with respect to and also be in that integrand, or not the integrand, but be one of the limits of integration. So as a result, we typically choose a different letter. In this case, we'll choose u to represent that. So we say that s of t is the integral from a to t of r prime of u du. But you compute this the same way. You just end up plugging in t once you're done integrating and then subtracting that starting value at a. And if we do this, it's something called the arc length parameter. And it's going to help us understand how that arc length function changes over time. And you might ask yourself, well, why would we want to do this? Well, for one, it's always nice to, instead of having to say, I want to compute the value from the starting point to, if I want to go from 0 to 1, I have to compute it, a whole integral. If I want to go from 0 to 2, I have to compute a whole integral. 0 to 5, I have to compute a whole integral. Instead, I can develop a function so that I can just plug s of 1 gives me that arc length. S of 5 gives me that arc length. So I don't have to do this a bunch of times. But it also has an interesting theoretical result. And if you go all the way back to your initial studies of calculus, there was this idea of the fundamental theorem of calculus. And there were two versions. But one of them said that if I have some sort of integrated function, or some function I'm integrating from a to t, so this parameter, and I end up taking the derivative with respect to this parameter, it's similar to just subbing in the parameter for the initial function. So you're like, well, why would I want to do that? And for this case, we're looking for that special relationship. We want to show that the derivative of the arc length parameter is actually this function, that magnitude function. And we're going to be able to use that as we go along to derive some interesting results that related to arc length.